Good evening, everyone. We have a very special guest tonight who is very generous with her time. She was actually going to teach a class for me tonight when I had to be somewhere, but that thing got canceled for me. So Ms. Katoum is here. She is co-directing the whole entire course, and so I'm learning some things about the course from her, and we're working together and developing a lot of the materials of the course. So tonight's class is going to be to help shore up or build some of our skills in ions and putting ions together to form molecules and how we name those and what all that means. It also ties in very well with what you're doing in the lab. So your workshop before lab is a lot of the things we'll talk about tonight, and then it builds, both of them kind of build on each other. So it doesn't matter if you have it before or after. Hopefully they'll be synergistic and both help out with the other one. So Ms. Katoum is going to start us off, and it'll kind of be both leading class today.
Or do you just swipe on this, or how do you touch like that?
Yep,
Gotcha.
and then if you want to draw,
Thank you.
when you draw, you have to take your pencil and
Okay,
then draw.
cool, because mine's a little different. Okay, good evening, guys. I'm so glad to be here and get a chance to talk to you. I've seen some of you in lab, so it's great that I'm seeing your faces in lecture, too. So after we're done with you guys should be able to, for any element, predict the charge if found as an ion, figure out how many ions or how many bonds it will form if it's sharing these electrons, determine the formula of salts from the name, and then we give you guys, we flip it the other way around, and then give you guys the formula and you determine the name, or we give you the name and you determine the formula, and vice versa, okay? So, you guys have kind of seen some of this stuff in lab already, so this is great, but we wanted to kind of get you aware. We keep noticing a pattern in nature, and it turns out that the alkali metals, which are group 1As, tend to form bonds with the halogens, which are group 7A, and we typically find them in this like 1-to-1 ratio, and they seem to look similar. So they're stable white crystalline solids. They have very high melting points, and they're soluble in water, and if you take their solution and you dissolve them in water, they seem to conduct electricity. So we start to think, okay, what kind of patterns are we observing based on what we're seeing on the periodic table? And some of this, I'll give you examples of that. So like potassium iodide is found, where do you see potassium iodide? And salt? That's right. Why do they add it to salt? What do you think?
So it won't break down.
So it won't break down? I haven't heard that one before. What else? Because your body needs iodine. Now, does your body need the iodine like elemental iodine or the ion iodine? The ion. You don't want to have elemental iodine. You don't want to eat elemental chlorine. It's a toxic gas, right? But what you need is the ion, but you don't find, like, we don't have iodide ion just swimming around in salt. We put it in as potassium iodide. And yes, you need it for the thyroid gland, okay? It's very important that you have that. Another example that you kind of need for your health is sodium fluoride. Where do you find that? Toothpaste, good. Where else? Water. And they do have to add it to the municipal water supply because it does protect your teeth against cavities. So that's kind of cool right there. But again, you don't want to eat elemental fluoride. You don't want to put that on your teeth, okay? It's the fluoride ion that's needed. Sodium iodide, we'll talk, I don't know if Dr. Bailey, when we get to nuclear chemistry, we'll talk a little bit about scintillation counters and how that's found in there. So anyway, we keep seeing this pattern of this 1-to-1 ratio, and we're going to kind of get you guys to see. This is stuff that I always like to share with you guys. It's found in your book, but these are some of the ions, more ions that are needed in your body, so it's worth taking a look at. I don't know if Dr. Bailey will ask you guys exam questions. I like to ask some of these on the test, but that's just me. I'm not saying he's good at it. So we talked a little bit about if you put ionic compounds that are soluble, that they do conduct electricity. So what is electricity? Okay, take a hit on that. Flow of what? What do you think?
Energy through like electrons.
Energy through electrons, so it's the flow of charged particles that are free to move. So literally, guys, if you take salt and you put it in water and you put a probe in there with a battery, it will turn your light bulb on. And you guys can YouTube this. It's kind of a fun demonstration because there's flow of charged ions, okay? So we're going to take advantage of the fact that when elements combine together, they're going to, like a cation, a positive hooking up with a negative, they're going to create a charge-neutral compound because they will, let me say that again. I said that wrong. Here, we usually dealt with atoms that are neutral, but now we're going to deal with atoms that are charged that get together to form compounds that are neutral. All right, so I think Dr. Bailey's going to take it away from here since we introduced these ionic compounds to you.
Thank you for the introduction. And I'm going to move the clicker thing. Somewhere there's a device. We're going to start out with some warm-up questions. Hopefully these are somewhat comfortable. Can I ask that everyone put this sheet away if you have this out? This is a sheet that you got in workshop. You also got it in class. On one side it has electronegativity values. The other side it has polyatomic ions and it has charges across the periodic table. Put that away. I want us thinking about how we can figure stuff out that's on that by working through it question by question. All right? So talk to your neighbor if you're not sure what these terms mean. We know the terms mean? Look there, I thought terms. Sorry, we'll have some terms coming up in the next question. Couple more seconds. We go all the way down to 0. All right, I'm going to go ahead and close out. Has everyone submitted their response? 51 today. All right, we're closing out. Whoa, did I double click? Is that a new question?
Same question. Same question.
I know, but I think I hit it twice. Maybe? Is it frozen now? Don't click in. Don't respond, please.
I usually go delete that one when I do that. I do that all the time.
Why is it not letting me stop it? All right, can I get an explanation while I deal with the technology? Why did you answer the way that you did? Volunteer. Jocelyn? How many electrons would it have to lose versus how many would it have to gain, and why would it lose or gain electrons at all? Why?
So what noble gas would it look like when it loses 2? Why not go the other way? So to go from calcium to krypton. That's a lot more, right?
I don't know what is going on with that today.
You broke it last week.
Keeps on saying there's a poll going.
My attendance just went.
Start class. All right, I'll adjust those afterwards. Still frozen. Awesome. Fantastic. All right, we broke eye clickers. We broke it permanently. So I like the comparison of noble gas, right? So we're thinking about where are these elements compared to noble gas. And do you remember the stuff we did on exam 1? I know it was like a long time ago. But if I asked you to give me the electron configuration of calcium, could you do that? So does anyone want to try reading it out off the top of their head?
Oh, we're doing it like that.
2s, 2.
2p. No.
2p6.
3s2. 3p6 and 4s2.
So where is the noble gas configuration that's closest to that? Right on different sides of the room, so you get double vision here. So that is why calcium is likely to form a +2 ion. If it gets rid of these two electrons, then it has the electron configuration of a noble gas. And so I want us thinking about quantum is kind of our definition for what are the stable elements, what do we need to do in order to get there? Do we just gain a couple of electrons? If we wanted to gain electrons, how many does calcium have to gain to be like a noble gas electron configuration? You have to gain 6 valence electrons. It would actually be 16 total electrons to definitely be able to d electrons, but that would be just way too many. So we're always going to think about the elements on either side. We want to be able to predict, based on their electron configuration, how far they need to go, gaining or losing electrons to be like a noble gas electron configuration. So what are we going to call calcium when it becomes an ion? And we're going to do old school. We're going to do 1 or 2 instead of A and B. 1 is answer A, 2 is answer B. So think about it for a minute, check with your neighbor, and then say if you want to be secretive about it, you can put it up to your chest here, your throat. 1 or 2, 1 or 2. All right, go ahead and put up your vote. 1 or 2. I see a little bit of a mix, but I see a lot of 1s. Anyone want to say how they remember which one this is? Okay.
It would lose 2 electrons, which would make it more positive. So it would be a
So why is cation positive? I agree, but how do we remember that? Does anyone have tricks for remembering that?
Positive and cat videos on the internet are positive.
Fantastic, if that works for you. Ada? So that's how I remember it, is that the cation is the only one that has a plus-looking letter in it. And so it's easier to look at and just be like, oh, this one has the plus in it, has the T. But however you want to remember, that's fine. So cation is just a word to describe positive ions. That's it. It's nothing fancy. So then what are anions? Negatively charged ions. And if they're elements on the right side of the periodic table, what do we call all those anions? What do we do about change the ending to? I'd. So I, when we see it on the end of a name of an element, means it's a negatively charged ion. So what would oxygen be if it's a negative ion? What about fluorine? Okay. So you get the trend. So if you see it as a negative charge, does that mean it's a -1 charge? All right, so we're going to spend some time kind of thinking about that as we go forward. We can't really click this in. Do we know exactly what charge calcium is going to be if it forms an ion? Why is it 2+, Carmen? It's in group 2. So what does that mean? If it loses 2 electrons, it becomes more like a noble gas. Okay? So I want to be really careful, and we don't want to say it has to lose electrons. All of these elements we're talking about can lose electrons. But we can also find it with all of its electrons, and it's the solid metal. Calcium metal exists. It is somewhat stable. Magnesium metal exists. Does anyone know the examples of where you see magnesium metal, not the ion? We have any car buffs? People that are into fancy things?
Is that what you use as a fire starter, or am I thinking something else?
Yeah, so you can actually use magnesium as a fire starter. I think if you light that up, then it goes off like crazy. It also is found in race car wheels, but because it's a fire starter, if you get the race car disc brake too hot that's right beside the wheel, if that wheel catches on fire, the whole car, you can't put it out. It just burns to the ground. Because once it does ignite on fire, it's really terrible. So you can find them as solids. But if you do find them as an ion, the question is, do we know how many electrons they're going to lose or gain to become that ion? So that's what we're kind of focusing on tonight.
Did you guys see magnesium in the lab also?
You had a good fire starter.
You did the same thing in lab. You ignited it, right?
Okay, so why don't you, if you have not already, go ahead and fill out the next 3 questions. I'm going to try to reboot the iThinker software because I want to try to use this in class. Yeah, there's one. Thank you. Maybe. All right, go ahead and submit your response. We're going to do these relatively quickly since you've already kind of worked through some of them. Yeah, go ahead and click in your response.
Is that what you mean by formula? Mm-hmm. Oh, okay, cool. You look really nice today.
I'm not able to check in.
No, only check in now.
Is your Wi-Fi on? That might help. All right, we got 42 responses. Everyone got a chance to click in? Closing out. All right. So we have a vast majority of students answering that sulfur is going to gain electrons. Why? Can I have an explanation? Can I have a volunteer? Yeah. Here. Okay, so in order to become the next noble gas, might we change that a little bit? So is sulfur going to become a noble gas? No. It's not going to become it. It would have to gain protons if it did. So what's going to become like the noble gas? The electron configuration. So let's just be really careful in our wording. We're not turning sulfur into argon. We're turning it into the electron configuration of argon. So in order to do that, it would have to gain electrons. I absolutely agree. And then that makes it a 5-second question. Closing out. Look at y'all. I've been the fastest we've ever answered a question. And we had 90% agreement. Does anyone argue why? Because that's what it's called? Yep. So negative charge means it becomes an anion. So it gains electrons. It becomes an anion. So then our charge that we're going to have on that, what is the exact charge that we're going to have on that sulfur? And then what's it called?
It won't let you type it.
I'm not going to type in both of those, but oh.
It only gives us like.
Fail. Okay. Sorry, numeric answer is open.
Invalid.
Okay, Derek.
Couple more seconds. 43 responses. Closing out. Okay, so what is the kind of general rule? Our majority answer in this case was -2 is the charge that we're going to have on sulfur. Why? How do we predict that, Shelby? Do you have a question or something else?
It won't let you type it in like that.
Yeah, clickers are kind of picky. So I just want you to know that it has a -2 charge. You can write that either way in my mind. In my book, mastering is picky, though.
Mastering, guys, if you're doing that, it wants you to do it as 2 minus, so be careful. It won't let you do minus 2.
So important to keep in mind. Okay? So what's the general rule that helps us figure that out? How can we answer this really quickly if we don't want to write out the electron configuration every single time? What group it's in. So what group is this one in? Group 6A, main group 6. So if it does form an ion, which it does some of the time, does it always have to form an ion? It can also share electrons, and then it will also look like it has an octet. How many electrons would it have to share to look like an octet? Same number. So let's keep that in mind. One of the main take-homes I wanted today was for you to think about, we can find elements in ions. We can find them in compounds that are not ionic. And they're molecular bonds in that case. So it doesn't have to be always the ionic form. So which of these is an appropriate formula for a neutral salt that you form between those two elements we've just been talking about? Try to answer on your own first, and then compare with a neighbor. How are you answering this?
So it would be neutral.
How do you get to your answer?
Because if it's
But if
sulfide,
you're reading,
the sulfur's
if you're
going to lose,
reading,
that means the calcium's going to gain. Right.
so yeah, that would be.
So you're going to have a salt which has a positive and negative. Which is positive, which is negative? Based on all the stuff we just talked about.
Okay.
And then what's the charge on each one, and how many of these do we need to make equal? All right, we have 53 responses. Did you check with your neighbor? Do you both agree? And if you don't agree, I want you to argue it out. All right, so I took a look at these answers, and you know what? The approach that I use gives me this answer C. Is that right? Why? What's wrong with answer C, Morgan?
Well, you ask for the neutral and they both cancel each other out, so you don't need that.
So if we're only worried about having a neutral salt, by definition that means we have the same number of pluses as we do minuses. Is this answer okay?
Yes.
As far as that description is concerned, absolutely yes. Because each calcium has +2, we just determined. Each sulfur has -2, so we have +4, -4. It's great. Why is that wrong? Chris?
Because it's the same thing as just putting 2 CAS, right?
So we always want to put the least number of each element that can form a neutral salt. So yes, if we go and we were in the Magic School Bus and we dove down, we could find calcium sulfide, and it would have Ca. If we look at a little block of it, we might find it might have that many in one little cube. But we're not going to say that that's the formula for calcium sulfide. We're going to say, what's the smallest repeating unit that exists? So we always want to use the simplest numbers that get us to a neutral formula. Questions on that? So if you have an approach that does something with cross-multiplying of charges, which is a term approach that some professors teach, I hate, because I see students with this answer, and they're like, yeah, I just cross-multiply the charge, and it's wacky. So I just want you thinking, what's the simplest way that we can have these two elements together and have overall no charge? That's what we want to do. So we're going to be practicing that a lot today. Ms. Katoum, do you want to talk through
Sure.
how this builds off what we've been looking at?
So, we're just some examples similar to what we were talking about. So if you look at just the sodium atom, guys, we think, okay, it's got 11 protons that are positive, and it's got 11 electrons to counterbalance those out and give you zero charge. Okay? So we did a bunch of that in Unit 1. Now we're looking at potentially, if sodium were to form an ion, you can tell how many valence electrons does it have there? The sodium? 1. It's like on that third floor, if you will, right? You've got 1. So it can do one of two things. To get to the octet, it can either gain 7, you see that? Right, to get the 8, or it can knock out that 1 on the third floor, and the next one, the second floor, will have a full octet. So it's easier to knock out 1 electron than to gain 7, and so we see the sodium cation form like this. Now, check this out, the difference between this. If you say the sodium atom, there is no charge as a superscript. Superscript is the charge. Here, if there is, notice there's 11 protons and 10 electrons, 1 more proton than an electron, so you get the sodium plus. Do you have to put a 1 up there? No. Yeah, because that's just assumed to be there. Okay, now let's look at chlorine. So if we're talking about the chlorine atom, this is its electron configuration. On the highest floor, or shell, if you will, or you can think about it like an orbital in the solar system, you've got 7. Okay? So you can do what? What are 2 ways to get a full octet? You can gain 1, or what is the other way to do it? You can knock out 7, which is easier. Gain 1. So chlorine, if it were to gain 1 electron to get 18 instead of the 17, it is called the chlorine anion. And we'll show you guys, it's actually called the chloride ion, because you change the "ine" to the "ide" when it is an anion. And so you put a superscript as a negative right there. So I think, do we have a slide after? Let me see if we have.
I think we get to that.
We get to that. Awesome. Go back. Go back. There you go.
So with this representation, what is the element or ion depicted here? This is a multiple choice clicker question. And I want to hear the justification for why. Check with your neighbor after you determined your answer. Oh, watch it though. Watch it. A couple more seconds. Could I have a very brave soul that changed their answer? About a third of the class changed their answer once they started talking. Who is willing to share what they picked at first and then why they changed their answer from that to something else? Be brave. Eleanor?
So originally I put what's called neon because I wasn't paying attention. I just thought, oh, 2s2, 2p6. But then I saw that you have 8 protons, and so I'm like, oh, it's oxygen that has a negative 2.
Great.
Yeah.
So I think a lot of people did that. A lot of people put neon at first because they just looked at the electron configuration. We have a total of 10 electrons. We have a configuration of neon. But what we've been talking about is that elements, if they form an ion, will strive to form an ion that has a configuration of a noble gas. So yes, it's going to have the electron configuration of a noble gas. But it's defined as being oxygen because it has 8 protons. But it has more electrons than protons. So it's going to be 2 minus, right? Is that what we said?
Yes.
So it should be 2 minus. We wrote that inappropriately for mastering. Mastering would have counted us wrong on this answer.
My high school teacher taught me that way, and I can't shake it. So.
Fail.
Fail.
You want to go through this one?
Okay, so we talked about, guys, the sodium cation forming and the chloride anion forming. So you formed that cation here.
Sorry, I have the.
I like So, when you guys knock that out, you see how you got that? We put that in there, although you don't need to, but we're showing you that the 3S.
My bad.
See, I'm not doing that.
That's my fault. Go ahead.
There you go. So you see here, again, we're just showing you that we knocked that electron out to get you the sodium cation. And here we're showing you how an electron went in. So guys, where did this electron, think about it, transfer? Electrons transfer. Where did the electron come from and where did it go? So it came from sodium and it seemed to have gone to chlorine. So in that case, that's what happens when you form these and then you get the sodium cation and the chloride anion. And that is why we see them happen. So I don't know how much you guys talked about, but remember chapter 4 that you guys did molecular compounds in lab? That was experiment 3 as well. You guys were talking about not electron transfer, it was about electron sharing. So I have an electron, you have an electron, let's make a bond, okay? But in this case, the difference between ionic and molecular compounds, or the molecular compounds that are made of covalent bonds, is that here you have a complete electron transfer, okay? So once you do that, you've got a cation and an anion. Now, you all know positives attract negative, right? So that's called electrostatic forces that kind of get them to combine. So here's a cartoon version of that. Again, kind of like Dr. Bailey was saying, if you had the magic school bus and you zoom in on this, you're going to see this crystal lattice structure of the chloride anions nestled here. In between them is the sodium cations. So again, you're zooming in on just one of these salt crystals. And look, it's not that we're saying there's one sodium and one chloride total. We're saying the ratio of sodium cation to chloride anion is 1:1. Now you could have a kajillion of these. I don't care. It could be like a million and a million. It cancels out to 1:1 ratio. Cool? So that's how we end up getting the formation of ionic bonds.
So if we put together, if we asked you NaCl, is this an ionic compound or is it molecular, meaning that they share electrons? How would you be able to answer that if you hadn't had this explanation? So either way, it's going to be neutral overall. How do we know from what we've learned the last week that that is ionic? Rikaya?
It's made of a metal and a non-metal.
Great. And so can we elaborate on that some more? What properties do metals and nonmetals have that we've spent a lot of time focusing on? So I heard the term polarity. Is that a polar bond? Superpolar. So polar, we call it ionic. Okay? So all this kind of comes together, and that's why when we see these two, if they were closer in electronegativity, they would share those electrons, that electron and this electron, and then both would have an electron configuration that was more stable, although sodium usually, it's a little complicated, okay?
Yeah.
But if we have two atoms that are closer together in electronegativity, for instance, two sulfur atoms or sulfur and an oxygen atom, they would prefer to not transfer because their electronegativity values are closer together. So go ahead and complete these two phrases, and then we'll have volunteers read them out. So it's questions 10, 11. All right, we need another couple seconds to finish this. Okay, another 20 seconds or so. they start neutral? So we're saying if it starts as neutral, is a metal likely to gain or lose electrons? By metal, we're talking about everything on that side of your octave. Okay, so does that need to gain electrons? If you start neutral, does it gain electrons or lose electrons? Okay. All right, do I have a volunteer that wants to circle for the first line? Chris, were you volunteering for the first line? We'll have Sebastian do the second line. And then we'll do Sebastian, and then we'll look see if they agree with each other, and then if the class agrees with them. What do y'all think? Any disagreements? Okay, so is the final part of the statement? Why? What's really wrong about that always?
There's transition
So there's a qualifier to both of these statements, and that's if we find them as ions, they will do these things. But remember, you can have metal, magnesium, that is magnesium 0. It is not an ion. But if we do find it as an ion, it's going to follow these rules. Oxygen, in most molecules you find it, it has a 0 charge because it's sharing electrons. But if we do find it as an ion with something else, it is going to follow these rules. Okay? So this is like a third of the time for nonmetals, we find them as ions, and so these are the rules they follow. So just make sure that you don't say always, that always nonmetals will form negative ions. If they do form an ion, it will be negative. All right, so we're going to do a number of clicker questions about specific elements. So based on its position on the periodic table, what is the charge of an ion if we find an ion of iron? Go ahead and submit your response first, and then check with the neighbor after, please. Might have to take after Ms. Katoon. So you might just need to refresh. Yeah, once it refreshes, it should choose. A couple more seconds, submit your answer. What are you going to choose? What are you going to choose? Where do you have it on the periodic table? What do you have your headphones in for?
They're just in because I don't have my case. And if I
don't
throw
lose them,
them
don't
around,
lose them. Okay.
yeah.
What are you going to answer? If you haven't already, check the person next to you, see if you all agree. Shut up. All right. Do we feel pretty confident in our answers? Let me close this out. I'm going to take a look because I'm in the back of the room. What's up with that? Someone want to explain why we have this kind of smattering of the different answers, but then we have a lot of people are saying cannot determine without more information? Ryan, what did you guys discuss? Bradley, what did you discuss?
So, iron is in the transition metal group, so we know that it has
I like 95% of what you said. So I agree that without more information, we can't determine what it is, because that's the definition of the transition metals, that they can transition between multiple charged states. The one thing that I might slightly disagree with you on is that sometimes we will have a specific iron 2, and it will only have a specific number of counterions because of that. It doesn't always conform to the anion, but it will determine how many anions it has. Is that subtle difference? Make sense? All right, so we're going to do the lightning round here. I want you to click in what the name of each of these ions are. All right? So go ahead. We're starting. We're at 5 seconds already. What's the name of this ion? Halfway there. Looks like most people are on. All right, 5 seconds, check with your neighbor. And close it out. Super confident. All right. So our answer is one of the least chosen ones. Why? Why? Okay, so what are the really important components? Shelby, you want to talk us through why we would choose answer B? Boom! Okay, so you never put the Roman numeral if you know it can only have one specific charge. Group 1, you never put the Roman numeral. Group 2, you never put the Roman numeral. And then there's actually 3 others in there that you don't, but we haven't talked about those. Those are aluminum, zinc, and silver. 3, 2, 1. Always.
No.
3, 2, 1.
But what did you say about aluminum, zinc, and
Aluminum is always a +3. Zinc is always a +2. Silver is always a +1. Those are 3 that are kind of that middle area that are fixed. They're always going to be that charge. Okay, and then what else, Shelby? Besides the fact that it's not a transition metal, why did you pick B? So if I just said this is called magnesium, what would I be missing? The ion. So if I say that we have magnesium in this water, you would picture a solid chunk of magnesium 0, not magnesium 2+. Okay? Ready to do the other ones? All right, let's go.
In the middle.
And closing out. Okay. Anyone want to argue their answer here? Julia, thank you for volunteering. What did you answer and why?
I should C because it's a transition metal.
Okay, and?
And it can have multiple charges, so since it's +3, it's the 3 Roman numeral.
Okay, and if we had had this as an answer, would that have been correct? No, because that doesn't say an ion, so we'd have to make sure to do that. So, majority of the class agreed with you. All right, next one. We missed an obvious answer in this one. Should have been ion for the first one. Because we didn't have that as an answer. Closing out. All right. Anyone argue their answer here? Chad? That was a big eye roll.
It needs ion on the end because it's an ion, and it's oxide because it's and there's 2 charge. And
Great.
Isn't just the last 2 rows before the noble gas? What about if nitrogen were to form an ion?
I think it's the last 3 rows.
Any nonmetal.
Any.
Close, just adding on to that a little bit, right? So if I had this as an option, oxygen ion, would that have been correct? So by saying oxide, we know that that's a negatively charged oxygen. So with all those nonmetals, we want to put that I there. All right. You got the hang of this? All right, closing out. No, 55. Okay. Sarah, would you like to share what your group discussed?
I got confused, and I was thinking it was transition metal.
Why is that confused? What do you think? Is it transition metal? Yeah. So what are we calling transition metals? Let's make sure we're all on the same page. What's your definition of transition metal, Sarah? Perfect. Middle of the periodic table. Is this group a transition metal group? Nope. This one? No. But starting here, where do I stop?
You gotta stop here.
Okay, kind of. It kind of goes like this. So that red line is the distinguishing area between nonmetals and metals. And some of these in the middle we kind of call metalloids because they have a little bit of metallic property. But that's kind of our line. So that's why if you look at that, the one thing I do like about that table, this thing, that you all use for lots of reasons that it shouldn't be used for, is that you can kind of see in that bottom corner that there's some transition metals that have multiple different charge states that are cations that you can find in that. Okay? So it is a transition metal. So then what do you do as far as naming it? Roman numeral 4, and then you make sure to call it an ion. All right. How do you feel about naming of the ion itself? The question is, then we put it together in a compound, it gets a little bit different. There are additional ions that you need to know. What are those ones? What does that mean, polyatomic? Bing! Okay, so there are polyatomic ions that we do need to memorize for the test. Unlike all the ones we've been looking at so far, the ones we've been looking at so far are a single atom that is an ion. The polyatomic is a cluster of atoms that are not ionically bonded together. So when you look at them, you'll find like Cl O3 minus. That these are all these atoms in a polyatomic ion are covalently bonded. They might be very polar covalent bonds, but they're covalently bonded. Overall, it has a charge, so it is an ion. And then we're going to say this thing can form an ionic bond with one of the cations that we were talking about. How many do you have to memorize for the exam? All of them. And do you need, what else do you need to be able to say again?
And the Lewis-Dot structure.
And their Lewis-Dot structure. So I'm going to take a step back on that. What I'm going to change my mind about is all the ones that are bolded are the ones you have to be able to draw Lewis structures for. What you'll notice about those is the ones that are not bolded don't obey the octet rule. And we haven't really talked about that in this class. So you do not have to be able to draw Lewis structures of the ones that are not bolded. Any questions on that? You might want to highlight it on your list if you have your list. It's the same order as your list. So just put a little star. Basically anything with an oxygen, carbon, and nitrogen in the middle. And then cyanide is also carbon and nitrogen.
I also wanted to remind you guys, just in case your lab instructor didn't, you guys will have that bottom that you guys are working on. So that list, you will have it on your lab quiz for experiment 4. Just to help you out, because we know it was a lot of stuff in that lab, to give you guys time to absorb, but you got to know it for the exam.
You will not have this list on the exam, is what you're saying. You will have it on your quiz in lab.
Quiz in
You
lab.
will not have it in lab. In your
But if
exam.
you're Monday, then by then.
All right. So, one thing that's going to be very valuable is taking practice. Draw the Lewis structure. How do we deal with a negative charge when we're drawing a Lewis structure? Where does that play in?
Bracket and a negative.
So when we have a negative charge, let's say HCO3 minus, if we're doing the S equals N minus H, and we're trying to decide how many electrons can we put in that entire structure, we know that we have 1 valence electron from hydrogen, 4 from carbon, 6 from each of the oxygens, and then that negative sign tells us that we have 1 extra electron to put in that molecule. So that counts towards which of these 3 letters? That's our valence electrons, right? So that H, how many you have, in this case is going to be 1 more than all the valence electrons of those atoms. Jump off.
On acetate, you give us an or option. Which one would be more beneficial for us to?
They are the same compound, but sometimes if you have a complex molecule, you can write it where you can see the shape of the molecule. You have a carbon with 3 hydrogens connected to a carbon with 2 oxygens. Here, it's just saying how many carbons, how many hydrogens, how many oxygens. You get to choose.
See the second one in lab, and some textbooks will have the first one, so I wanted to include both in there so y'all can recognize it's actually either or.
So, up to you, but one might give you more structural information.
What is it? I just have a question. Do you have
Nice and loud so everyone can hear you?
I was just going to say, do you have another sheet that wasn't here?
I do. I'll grab it to you in a second. It also was one that was handed out in workshop, so you might have it there. Olivia?
We kind of touched on this in lab, and I just want a little bit of clarification. When do you have to separate the H2O and CO2? Like, is that only in lab for HCO3?
Oh, that's when you form carbonic acid,
Yeah,
right?
so that's a chemical reaction.
Oh.
And we'll get to that starting the end of next week.
Okay,
Super quick.
Super quick. All right. So to me, it was like really overwhelming as a student. I'm like, oh crap, I have to memorize all these, and it felt like there was no system. And then there's other bromate or iodate, and you're like, oh my gosh, that's a lot. But here's the system.
And I think this is in your workshop handout, correct?
It was, yes.
Yeah, I think it's literally
In your
the
workshop,
text from
too.
it.
So if you guys, those are great resource to go back and refresh for our exams too. So.
And I don't use those, so that's why Ms. Katoom wanted to use them.
Right.
So if it helps you remember and helps you figure out trends, that's fantastic. So let's go through a series of quicker questions that are going to be geared at helping us think about molecules and compounds. So this is one that we did, I think, at the end of last class. Is that right? I think I pulled this up like super quick. So instead of thinking about ionic compounds that just have 2 elements, we're going to include polyatomic ions now. If we have sodium carbonate, how many sodium ions are you going to find in that compound? Go ahead and click in your answer first, and then check with your neighbor. If you're getting stuck on this, please raise your hand and bring one of us over. We've got lots of help.
I'm good.
All right, a couple more seconds. Okay. I didn't see that. Come on, John Paul. All right, closing out. All right. We have a whole bunch of different answers. How do we walk through this? Can someone help us out with the process? Process is really important. Let's hear from a couple different voices if we can. Anyone who hasn't shared their thoughts yet. Go ahead. Thanks, Heather. Can you all hear in the back? Speak up a little bit if you could.
When my friend Lena described to me, because carbonate has CO3 2 minus, and to become neutral, it needs 2 plus, and sodium is positive, so we said 2. We need
Great.
2 sodium.
So I love the process that you're describing. So the first thing you do is you say, what are my 2 ions? You say carbonate, okay, I've memorized that because I'm ready for the test. CO3 2 minus. And then we know sodium from the periodic table is in group 1, so it's going to form a 1 plus ion if it's in a salt, which this is a salt. And then you say, how many of these do I need to neutralize this one out? So if you have 2 Na pluses, we end up with neutral salt. Plus 2 from the sodiums, minus 2 from the carbonates. So then what would the formula be for that? How do we write that out? Is that right? This says we have 2 sodium carbonates that are not balanced. That doesn't make any sense. So how do we fix that? Is it like this? No. This says that in this compound we have 2 Na pluses and 1 CO3 2 minus. All right. Do the next one. So if we're talking about calcium carbonate, how many calcium ions will you find in calcium carbonate? Jump on the help. So we just had 1 and 1. Next week.
I didn't look at my list. I didn't look at my chart. We'll see if I got it right.
But hey, we literally just used the same polyatomic mass. Same one. It's carbonate. So long ago. Okay. What's the charge on that? Oh, that's sorry, it's different. Never mind.
What they have tonight?
It is neutral.
So what I have?
So you always just need to think, how many of each do you need to get to neutral?
Is that everything?
All right, closing out. Anyone else want to add in? No? All right. Okay, can I get someone else, some new voice, to share how you would answer this question? Tara?
far as like how you write the formula?
Yeah, how would we figure out how many of them we need?
The Ca is 2 positive, and the CO3 is 2 negative, so you would just need 1 of each.
So if we have 1 of each of these, just like written right here, and we put those together, we're going to have a neutral salt. Questions on how we do that? Is it always this easy? Is it always like 1 to 1 or 2 to 1? No. All right, so let's go through and let's look at some of the more complicated versions of that. So we're going to start. We're going to start here and kind of go down the list. If you answer this question, look at the next few and try to write out the formula before I give you some choices. And if you're getting stuck at all, flag one of us down.
You guys remember to write on your sheets, because you're going to forget how you got the answer when you're studying for the test. So fill that out. Yes, go ahead. Oh.
Alright, please put this away unless you absolutely need it for the polyatomic ions. I do not want to see the table with all the charges because I think that table is more confusing in this situation. You should be able to pick all this stuff out for trends. If you absolutely need the polyatomic ions, you can sneak a peek. Alright, we have 50 responses to this question. I'm going to close this out. Alright, can I get someone to explain how they thought through this problem? Can I hear from a new voice? Jessica, you look so willing to talk with your hand over your mouth. Would you be willing to share what your group discussed, or you can pass if you'd like?
We, as a group, picked C because of the potassium. Sorry.
It's okay.
The carbonate has a negative 2 charge, so it needs 2 potassiums to cancel it out.
Why? What do we know about potassium?
As a positive charge.
So it's in group 1, has a +1 charge for every potassium. So in order to make that neutral, we'd have to have 2 potassium ions. And the way that we write that is that formula. Okay? Ready for the next one? All right, let's do 1 minute for this one at most. Actually, let's do 30 seconds for this one.
My brain.
5 more seconds. Feel relaxed tonight. All right, closing out. So Ankar, what did you choose for this question? What did your group discuss about this?
We discussed it all, but I just went with B.
Okay, why'd you choose B?
I mean, why not, right?
Donald, what are your thoughts on that answer?
Because they're both, how should I speak for the metals, and they're not super cold enough they should be.
So we will never form a salt between two cations. It will not happen. You can make an amalgam, a metal mixture like bronze or something, right? But it's never going to be charged. They're going to be neutral in that case. So this will not form at all. Two cations you cannot make a neutral salt out of two positive things. It doesn't happen. So that was kind of a herring. Even got to you, buddy.
That was a trick question. I saw the smirk on your face.
There was an answer that was correct up there. Okay, so let's go ahead and put in formula. You ready for some short answer here? So we've been looking at formulas as the answers for the last few. So now we're going from name, write in formula, and I want you to actually type it in.
How do you put a subscript?
You can't do subscripts, I don't think, so you're just going to have to do a number. Are there parentheses? Yeah, you can do parentheses, right?
Just no subscript.
So is this one just as easy as the other ones? No. Why? What's a little bit more difficult about this one? It's not multiple choice, that's true. Additionally, what else is more difficult about this one? You have to actually find some way, besides just more of this one, to find a neutral ratio. So what would the process be on this? Can I get someone to talk us through the process you might have gone through? Jocelyn, what's your process? Copper has a... Great. So we know that because it's Roman numeral 3, it's a transition metal, so it tells us it's +3. What's the formula for that? So if we do 1 to 1, is it neutral? So what'd you do? Okay, so you did like. What do y'all think about that?
I don't know if it don't look right, but it could be right. Why did it say copper is 3 when this chart says it's 2?
That's why I want you to put that chart away. So one of the reasons that I'm not a huge fan of this chart is because this is the most common ions, but you will find all kinds of other ions. And as chemists, we pride ourselves in being able to make other ions. So this is not the be-all, end-all. So I really don't want you using this as a guide, other than to say there are trends on the right side, on the left side, and in the middle, it's up for grabs. Matthew, you have a question? What are ions? Can someone give a really good answer for that? What are ions, Chris? Nice and loud so Matthew can hear us.
Any like element that doesn't have its original electron configuration.
Yes. So original electron configuration is not there. It means it has a plus or a minus charge on it. Does that help? Cool, man.
So that's the answer. What's the answer right?
So if we look at this now, we have copper plus 3, copper plus 3. We have 2 of those. And then we have SO4 2 minus, SO4 2 minus. Right? We have 3 of these, 2 of these. How many pluses do we have total? We have 6 positive charges. How many negatives do we have? 6. So that's the right formula. What's that? Jocelyn and Matthew answered that question. She brought her helper. It's kind of cheating. I think he's feeding her all the answers. All right, let's actually skip those. Let's go ahead and do, which question number is this? 24? Question 24. Strontium is the name of that element. If you have to sneak a cheat look at the polyatomic ions, do so, but don't do so for the metals. Only use the trends for the metals, please. All right, we're going to do this one relatively quickly. Ten more seconds to click in an answer. And closing out. We are split mostly between answers A and B. Which one is right? You literally hear A and B being yelled out. This answer follows a certain kind of naming that is used only for non-ionic compounds. If we have ions, we do not say di the anion. We only use this for non-ions. So how do we know, is it one of these guys? Because we know it's not a transition metal. So we know strontium,
it's an
38.
Oh my god, it's SR is what you're on my face.
Okay. So one of the reasons we put this question in there was specifically to pull out that when you are naming compounds that aren't ions, you have to say how many of each of the things you have in there. So the di, if you have 2 nonmetals together, you would use di or tri or tetra. But because we're doing metal with non-metal ionic compounds, just by knowing we have strontium, which has a +2 charge, and nitrite that has a -1 charge, we don't need to say di or tri or anything like that.
Wait, so when do you use the di again?
If they're not salts, if they're not ions, then you use those.
Non-ion.
Okay, so the last 4 questions on this are going to be really valuable to try to work through. Your homework has tons of questions on ionic compounds. I do have the deadline set to Tuesday night because the exam is Wednesday, and I do want you with some wiggle room. don't wait until Monday night to start this homework. You're really going to hurt yourself if you do that. Please try to complete as much as you can before the regular deadline of Sunday. And there might be a little bit we need to do on Monday, which is going to be on the stuff you did the pre-class quiz for today, which is balancing equations. Bye, Matthew. Thanks for joining us.
Thank you.